This video is looking at simple harmonic motion for Year 13 physics. So when we're describing simple harmonic motion, what we mean is we are talking about an object which is oscillating or vibrating, and when we talk about simple, what we mean is that oscillation is not complex. So for example, a complex oscillation might look like that, for example, which might be like a vibration if you were to bang a desk, or it might be an electrical signal that has a lot of interference in it. That would be a complex signal. So when we talk about simple harmonic motion, we're talking about nice sinusoidal or cosine type curves that are free from all of this interference that would otherwise make dealing with calculations and the situation an awful lot more complex. So harmonic just means that it is oscillating, and when we talk about simple harmonic motion, we usually talk about what we call free oscillations. So the definition of a free oscillation is that it's one which does not have a driving force to maintain the motion, and it doesn't have friction. And obviously in the real world all situations have friction, so that's a bit of an approximation. But since most oscillations that happen in our everyday lives happen so quickly we barely register them, it's usually a perfectly appropriate approximation. Now there are examples when friction does make a significant difference, and we then talk about damping, which we will do a separate point to this. But if you have an object that's damped, you do need to reinforce that oscillation with a driving mechanism. So some things you should be aware of from when we've studied waves. So this is a displacement time graph for an oscillation that's undergoing simple harmonic motion. First of all, if I consider any point on the wave like this, then that distance from the equilibrium position is called the displacement. Now the displacement can be positive or negative, because at some time later the oscillation could now be going in the opposite direction, so the displacement here would be negative. The amplitude is the maximum oscillation, and the amplitude is always positive. It always has a positive value. It's not a vector quantity. Now on this graph, because this is a displacement time graph, the distance between two peaks is the period, which is obviously measured in seconds, not the wavelength. Remember that we can work out the wavelength from this because we have the equation period is equal to 1 over frequency. If I know the speed of the wave, then I can use wave speed is equal to frequency times lambda, or wave speed is lambda over period, which would be appropriate, and so I can work out wavelength that way. So just be careful that if I have a displacement time graph, then this is the period, not the wavelength. So obviously we also need to know the definition of frequency, which is the number of waves per second, and we need to remember this equation. Now when we are talking about any object that's undergoing simple harmonic motion, we use an equation that looks like this. So the displacement is a function of time. So this brackets t just means that the displacement changes with time. So you can see that as the time goes on in the x-axis, the displacement is changing at every point. So mathematically we don't need to really include this for what we're concerned with, but you need to be aware that displacement does vary on time, so that's why I'm including it at this point. Now if I wanted to work out the displacement at any point, I'd need to know what the biggest possible displacement would be. So what I do is amplitude multiplied by sine theta. Now theta here, it needs to be in radians, because obviously one complete oscillation represents 2 pi radians. So theta here how far through the cycle in terms of radians depends on the frequency of the wave and the time. But more specifically, because it needs to be in radians, it depends upon what we call the angular frequency and time. And I could also include a factor here, phi, which would be the phase difference. So this is our generic equation for a wave. Now I could also have the same expression but with cosine here, because that would just represent an additional phase difference of 90 degrees. So cosine is also a solution to this equation. Now I'm going to simplify this. I'm not going to bother with phi anymore. I'm not going to worry about the phase difference, and I'm going to remove the function of t bit because that's unnecessary. And so we just have as our basic equation for displacement, so an object undergoing simple harmonic motion, x is equal to a sine omega t.